kid cry today. All right. But having said that, I acknowledge that from time to time I will make a kid cry, and I'm okay with that. I'm at peace with it. I say comforting things. I say, can I get you a cup of tea? Now finish what you're doing. Kid cries on an exam. I just say, like, okay, hey, listen. Let's take a minute. Let's just breathe. It's okay. It's all going to be okay. It's going to be okay. Let me get you a cup of tea. I get back to work.
I start with flattery. Then if that doesn't work,
Violence.
I start with crying. And then if that doesn't work, I just insult them. And
Got
make
it.
them want to cry.
Deal. I support that. Okay, so optics is the study of light, and specifically what light is and how it behaves. And these two things are really interesting because we've just said a lot of things about light. Light lets us see, which is pretty cool. But if we're not careful, too much light in your eyes can do what? Blind you. Light can help plants make energy, and it can warm us up, and it can help our skin to produce vitamin D. But too much of it, and it can burn you, give you skin cancer, damage you.
Why do we get skin cancer?
Did you know if your immune system figured out that your eyes existed, your immune system would attack your eyes?
I don't know if that's true.
I read
But
somewhere.
I mean, I guess if your immune system discovered anything existed, your immune system would be like, time to take it out. These are called autoimmune disorders, where your own immune system goes after you, which is bad. Yes?
Why do we get skin cancer?
Well, from a cancer lesson, we know specifically what happens is the high energy light from the sun, when it hits our skin, can cause damage to the DNA. And if it damages the wrong genes, what it can cause is it can cause those cells to start just firing and making new cells rapidly. So it's basically, light is very damaging to skin, which is why the skin is specifically designed to not live for very long, right? We're just always making new skin and killing off the old. But if during its short life skin cells get damaged in just the right way by light, then they can begin growing out of control, and that's skin cancer. Well, that's exactly what I want to talk about. It's a great question. And so I want to start first with a really simple version. What's light? Okay. What else? It must contain energy, right? Because we know that it can warm things up and be used to make sugars and damage things. And do we have a laser cutter down in the shop? I don't know if we do.
I know what it is.
We need to get one. But has anyone ever seen a laser cutter before? You can take a plate steel, big, thick piece of plate steel, and shine a light on it and cut it. So light definitely has energy in it, doesn't it? My student John last year, one day came in and he was like, Orlando, check out what I got. And he brought in this like hyper high powered laser and he was like lighting things on fire with it. I'm like, John, you can't no, give that to me. And I played with it all day. And I was like, John, you can't bring this in again. But first I played with it all day. But it was super cool. So light definitely has energy in it. Is that the same thing as saying light is energy? Because it's got to be a real specific piece of energy, isn't it? Because not all energy glows like light, does it?
It has gas too.
So what is light? Let me ask you this. Does light weigh anything? Does light weigh anything? If I turn the lights on, do you get pushed down a bit? Is it heavier in here? Maybe just a little bit? Maybe you don't feel it? What do we think? Does light have mass?
Wait, okay.
Does light need, like, sound? Sound, we've said before, needs, like, something to travel through, right? So, like, sound needs air, right? Or water or something. But if I sucked all the air out of the room and tried to make a sound, you wouldn't hear it. If I sucked all the air out of the room and a little light, would you be able to see it?
No, because we're dead and unconscious.
Well, what if we're not in the room? We're outside the room safely, or we're wearing masks. We have air.
You don't need.
Does light need air? Does light need something to travel through?
No.
How do you know that? Because you're right, it doesn't. How do you know that?
Because it's like its own thing.
What's one place we know that it travels that doesn't have any air in it?
Space.
Space, yeah. We know that. That's good. Yeah.
It radiates.
Yeah, good. So these are all things. Here's a really simple version of light. A really simple version of light. It's a form of energy. Yeah, you can write this.
You always write it. Which is okay for him. He's writing a writer.
Whoa, I do not kill. Unless I have to.
Tell me last year.
I just said unless I have to, in which case I will.
You stare and judge. There.
That's true.
You just did it to me.
That's true. That's right. So light is a form of energy that moves in any direction. Let's keep the discussion of jingle balls to English class, let's say. We're in science right now. Yeah. Did you not get a copy? Oh.
I'm sorry, it was an eye.
All right. So light's a form of energy. It can move in any direction. It can move through empty space.
It moved really fast.
Yeah. Right? So it doesn't require any kind of medium. It can move through some things. So light can move through some matter, but not others. What's an example of something that light can move through? Sorry? Sure, some plastics, right? Some plastics. Light can move really well through this plastic up here. What about this plastic here?
It'll still move.
Kinda,
but it won't move
right?
as well.
Is it getting through this plastic? Yeah, definitely. Is it getting through the plastic as well as it gets through this plastic?
No.
No.
It depends
And
on
what's
the
something that it goes through a little bit better?
glass.
Yeah, this glass.
Don't start a fire. Be careful.
Yeah, that's not
That's
Stand
bad.
on the desk.
All right, I'm too hefty for
Stand on
that.
the desk, like you always.
But if we look here, can we see what it's like? The light is definitely going through my magnifying glass, right? Hey, do you see what other lights are going through the magnifying glass?
Glares.
You don't see that?
A little pixel.
That when I focus it, it turns into a perfect image where we're getting just the perfect circle there, but also it's focusing all the overhead lights. Can you see that? Do it again. I love this.
Oh yes, I see it.
Right? Oh, look, there's all the overhead lights. We could do that here on your desk, right? Like if we went like this, if I focus it, right, you should be able to see the overhead lights.
Oh yeah.
Right? Like,
Is that it?
focus.
Oh my god, that's cool.
Right? Who else? You guys are actually closer.
Light my paper.
Right, look at that. You can actually see it, like the plastic and everything. Isn't that kind of cool?
Light paper. That one.
Whoa, out of focus.
Like,
Oh, in focus.
wait, make it like light my paper on fire. Hold on, wait. I want to test something.
Oh yeah, we'll light some colors.
Oh,
Color. We will use the sun to do some damage later.
We don't shoot that.
I know, doesn't it? Same thing, because you're not seeing the first. See that? Those are the lights right behind you in focus. This will work much better because we're in the right spot. But look. There's the overhead lights, just like that. Right? You can see all that. Oh. So light can go just right through this glass. So we'll talk about that. It can move through some matter, but not all. It can be made to change directions. What's something that changes the direction of light? Yeah, a mirror, for example, right? If you set a mirror up, you, go away. All right, story checks in.
You want to read them?
No,
Okay. Are you sure?
not interested.
Why? It's actually very interesting.
No doubt. So, you should not write notes on your phone, by the way. It's a terrible way to learn. Every study shows.
No, it's not. It's like I have to copy it over to your doc.
I understand. I'm just saying.
Little quick facts.
I'm just saying that, like, and your teacher shouldn't give you assignments like that to do because all the studies show that we just do not learn well by typing. We do not learn well by putting things into our computer. It's just, I understand, which is its own fundamental problem. But just to be clear, like, you know, and the fact that our education system continues to give you these digital assignments to do when every piece of research says these things work dramatically worse than like just working out of books and with paper, it's a disgrace. But anyway, that's a different discussion. We'll get back to that later. All right. So here's some stuff we know about light. How does it move? Well, like we said, in straight lines.
It doesn't move. That's a joke. It doesn't move.
Straight. I'm having a moment. Straight. STRAIGHT. Can somebody Google that for me? I'm having a moment.
You're right. You're right.
Why does that look so wrong to me today? That's correct, right? Yes, you may. So it moves in straight lines, unless made to change direction. So light will move in straight lines unless it's made to change direction. What are some things that can make light change direction? Somebody already mentioned one of them. What could make light change direction? A mirror. And what do we call it when light hits a mirror and changes direction? We call that reflection, like a mirror. Good. All right, what else? A mirror or something else. It doesn't have to be a mirror, by the way, because even like this guitar isn't a perfect mirror, but it at least makes some of the light change direction, right? See how you can kind of see your reflection or I can see your reflection in the surface of this guitar, right? Because it's kind of, mirrory enough. It can make light reflect. We'll talk about how even things that don't look mirrory at all are making light reflect, but that's okay. We'll talk about that later. That's good. What else can light do? Does this make light reflect?
Yeah. No.
I mean, maybe a little bit if we look across it this way, but most of the light goes through it, right? And yet, it's doing something to the light, isn't it? Because normally, does this light make a perfect picture of itself on this table? No. But if I go like this, it does. So what's going on there? Well, it must be taking the light and making it change directions. Does that make sense? So how is that doing it? It's not reflecting it because it's still going through. Reflecting means like bouncing back, right? But here it's passing through, but bending it. So we can reflect light. We can also bend it. Does anyone know what that's called? It's like reflect, but it's, maybe you've heard this word, maybe you haven't. It's okay if you haven't. We'll talk about this unit. Yeah, refraction. Refraction means not like bending, not coming back where it came from, but just changing course slightly. This is a weird one. Gravity. Light actually does respond to gravity, but not by falling. Gravity, you don't have to worry about this, but Einstein's theory of relativity tells us that the way gravity actually works. Does anyone know how gravity actually works? We know what it does. Gravity pulls us down, right? Do you know why gravity pulls us down? It's actually really cool. Because everything that exists in space causes space itself, space and time. This is weird, itself to bend. Weird, right? But you know how you put like a bowling ball on a mattress? The mattress sags down? Yeah. That's just an analogy. Or you put something on a trampoline, the trampoline kind of sags. If you put something that has mass in space, space bends. Weird, right? And the heavier the thing, the more space bends. Make sense? And so that's why you fall towards the Earth, because you used to be on a nice flat space time, and when the Earth sits there, it bends space-time so it's on a curve, and you fall down the curve. That's it. That's what the theory of relativity tells us. That's weird. There's a lot of math involved in that, by the way, so I'm giving you like the analogy and not all the math that gets you there. But the interesting thing is, anything with mass causes the whole universe to bend around it, and heavy things cause the universe to bend a lot. You cause the universe to bend just a little bit. The planet Earth makes the universe bend quite a bit, which is why we fall towards it. The sun, for example, makes the universe bend a lot. Black holes weigh more than our sun and are tiny. Oh man, that rattling is crazy. You can all hear that, right? That like low thrum, but then now the door is going with it. So anyway, a big sun in the sky actually does something called gravitational lensing. So you want to know something really cool? We can actually look out, and where there's a black hole or something like that in space, we can actually see what's behind it because the light behind it goes kind of like whoop and gets lensed right around the black hole. Kind of a cool thing. Not something you need to worry about much in this course. We're not going to talk about black holes and gravity and things like that, but it is an interesting thing to know that gravity itself can make light bend, even though light doesn't have mass, which is something we might have wanted to mention, that light doesn't have mass. That's because gravity affects things with mass, but it doesn't only affect things with mass, because it actually is the bending of space-time itself, bending of the universe. Light is this, no, we're going to talk about this really interesting property. So, there we go. Now, how fast does light move? If I turn on the lights, is there a delay between when the light is there on the bulb and when the light gets to my eye and I can see light? It doesn't get to me instantly? How long is that delay? A couple seconds. A couple milliseconds. Milliseconds is a pretty long time by standards. Like, it's weird. Like, how long does it take? Like, if I had a really fast camera, would the camera be able to, like, take a picture where it was like, oh, there's light here, but none here. It's still dark here. And then, oh, there, right? I mean, it actually would. Mind you, you couldn't do it with a camera because by definition, cameras use light to get information. And so, you know, like, they can't be faster than the light is. But it does take time to get to me. It is for a brief instant, there's some light here, but none here, right? Which is if I had my hand out, my hand would be bright, but my arm would be dark. That does happen, but it happens real quick. Like, real quick. How quick? Well, we'll look up the real number in a moment, but about 300,000 kilometers every single second. So that's a long distance. But it's not like that long a distance. You know what I mean? Like, if we look here, that means the light on this side of the sun, or in the middle of the sun, actually takes a couple seconds to get to the edge of the sun. Is that kind of weird to think about? Right? The sun is so big that it takes a couple seconds for light to get from one side of it to the other. How long does it take the sun's light to get to us? Do you know? Do you know how far we are from the sun? On average? Oh, that's actually a little creepy, and I'm sure my computer is listening to me right now. It's about 140 million kilometers, and light only travels 300,000 kilometers a second. So that means 300,000, 10 seconds would be 3 million, 100 seconds would be 30 million. So we're in the order of about like 800 seconds. And in fact, it takes about 8 minutes for the sun's light to get to us, which means if somebody shut the sun off right now, you wouldn't know immediately. It would take you about 8 minutes to find out, because that's how fast it takes the light to get to us. Speed of light in kilometers per hour, or in kilometers per second, is 299,792. Now, the thing of it is, in science, we tend not to use kilometers, we tend to use meters, all right? So, we're going to say it's about 299 million meters per second, or about 299,000 kilometers per second. Does anyone remember scientific notation from grade 9? Grade 9 math, grade 9 science? Caitlin loves scientific. Caitlin, I said Caitlin as if that's your name, which it isn't. Caitlin loves scientific notation. That's cool. I do too. If we wanted to, remember, scientific notation is just about taking a really big number and just making it so the decimal comes after the first one here, and then saying how many times we had to move that. How many times did I have to move the decimal place to get it there? 1, 2, 3, 4, 5, 6, 7, 8. So you'll sometimes see this written as 2.99 times 10 to the 8 meters every second. You don't have to stress about scientific notation. Look at me. In this course, if at some point a number is written in scientific notation and you don't know what that means, you know what you can always do? Just put your hand up and ask. But do we remember in general what scientific notation means? It's how we handle big numbers. And basically this means move the decimal place this many times. Our decimal, there's 10 numbers in a single decimal place, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have to go to the next decimal place. Does that make sense? So this just says add another decimal place. And how many times do we need to add another decimal place to this number? 8. That's all. And this is actually easier to write than that, even though it's almost the same number of digits, because I don't know about you, but when I see a number with a ton of zeros and I try to rewrite it, you ever miss one or add one? I do all the time, right? Whereas this just says, it's like this number, only the decimal is actually 8 over there. And what would I do if I wanted to make it be a decimal number? Don't worry about it, but if I wanted a decimal number but a really small one instead of a big one, like how would I write that? I'd write that as 8.4, but then how would I say, the decimal should actually be over there? How many times does it have to move? 1, 2, 3, 4, 5, 6. How would I write this and say move the decimal 6 times, but know that this should be a really small number, not a really big one? What do we do to this? Yep, and how do I show that with an exponent? You're right that I could say divided by 10 to the 6th, which would actually be even better, but that's not what they do. That would be better scientific notation. But instead, they do it in the exponent. And what kind of exponent means divide? Yeah, good. Very good. Anyway, you don't have to worry about that. This is really fast. Really fast. That is fast enough that in day-to-day life, it is effectively instant. Does that make sense? Like, for all intents and purposes, in your life, you are never going to have to think about, but how long does it take the light to get to me? Do you know what I mean? Like, when you turn the lights on, you never think like, light on, it's going to take a few seconds for that light to get over to me. I turned the lights on, but the light is closer to Aiden than it is to me, so Aiden's going to be seeing things before I see things. It just doesn't work that way, right? Like, it's so fast. Even to the point of on a big scale, what's something that's much slower than light? If there's a lightning bolt that hits the ground, that light gets to us super fast, right? It can travel around the Earth like 50 times in a single second. Lightning gets to us super fast, no issue. What's much slower and takes a while to get to us? Sound, right? You've experienced that before. Sound moves a lot slower than light. Light is effectively instantaneous here, but on a big scale, I'm going to say on a big scale, this number matters a lot. For example, 8 minutes for sunlight to reach us. Which means when you're looking at the sun, which, don't stare directly into the sun, you're looking at how it looked 8 minutes ago. You can't see what it looks like right now. You can never know how the sun looks right now. You only know how it looked when it made the light that you're seeing. But it's a bit more interesting than that, too, because what else moves at this speed? This very specific number, 300,000 kilometers every second, 300 million meters every second. What else moves at that speed? Electrical signals. So maybe you're like, hey, I want to know what the sun looks like right now. So I'm going to put a camera there on a spaceship and we'll run a wire, right? And so we'll run a big long USB cable and we'll take a picture. So now we can see what the sun looks like right now. No, you can't, because how long does it take the signal down the wire to get to you? Same 8 minutes. Does that make sense? An electrical signal can't move any faster than that speed. That's the top speed. Radio signals move at this speed. So we say, okay, no problem, I'm going to put the world's biggest Wi-Fi router out by the sun. We'll take a digital photo and we'll Wi-Fi it to us. Still take you 8 minutes to get that information because it takes that long for there. There's an interesting case. This is what's really weird. The sun, in addition to shining on us, also makes the Earth spin around it. Why? It has a lot of gravitational pull. Good. Gravity moves at this speed. If a magician made the sun disappear and go away right now, not only would it take 8 minutes for the light to get to us, but it would take 8 minutes for us to stop being pulled by its gravity, because we're being pulled by the gravity that the sun made 8 minutes ago. Which means that if the sun disappeared, 8 minutes later, Earth would go, phew, and just go flying off into space. Right at the same time we saw it go dark. Not instantly, because even gravity moves at this speed. The fastest anything in the universe can go is that speed. It's what we call the cosmic speed limit. In fact, it's as easy as this. Anything that doesn't have any mass can travel that fast, as long as it's not interfered with. Does that make sense? But as soon as you have mass, it slows you down. Does that make sense? So nothing that has mass can go that fast. You cannot go that fast, because your mass prevents you from moving through the universe at that speed. You can get very close, theoretically, but weird things start to happen. Very weird things start to happen. I don't have time to get into that. Take grade 12 physics. You'll learn about how if you got really close to that speed, your weight would start to multiply at an alarming rate, and you'd weigh billions of pounds before you knew it. But also you'd stretch out, so you'd be millions of kilometers tall. Going that fast does weird things.
I could be taller.
You can be taller. You just gotta move faster, kid.
I don't care. I'm going to space.
Yeah.
I will die tall.
Well, there you go. You want to know something else? Every time you speed up, your mass gets heavier, even by a little bit. You move a little faster, you weigh a little more. You move a little slower, you weigh a little less. It's so little that your scale will never notice, but it's true. Weird stuff happens. This is a weird thing, but this number is the cosmic speed limit. Nothing can move faster than light, and everything that has no mass moves at the same speed of light. Does that make sense? Yeah.
Sharpener other than your side sharpener.
I don't, I'm afraid. Does anybody have like just a good old-fashioned like ring?
Oh, there's one in my bag.
Oh, great. If you got that, Fraden. Okay, now, let's talk about this then. What happens to light when it hits stuff? Well, we've already said this. There's three things that can happen when light hits something. All right? Light hits something, what can happen? Well, first thing that can happen is it can bounce off. And we've already said what that's called. It's called reflecting. Now, that can look one of two ways. All right? On a nice smooth surface, like a mirror, if we have a beautiful smooth surface like this, and light comes in, my ruler is gonna get a workout this unit, comes in at, I'm gonna be physically accurate here, even though there's no reason to, it doesn't matter. Light comes in waves like this, or in rays like this, because we talked about how light travels in straight lines, then it will just bounce right off. Does that make sense? So the light comes in and it bounces out. And the light comes in and it bounces out. And the light comes in and it bounces out. I think I like the arrows just at the end better. That's the way to do it. Light comes in, light bounces off. Comes in, bounces off, comes in, bounces off. And that would give you like a mirror image. Does that make sense? Because the light rays, if you look here actually, this explains why a mirror does something we all know a mirror does. The light comes in, it leaves, and it looks pretty much identical. The only difference is it was going to the right, it was going down and to the right before, and now it's going not down and to the right, but on the way out it's going up and to the right. Does that make sense? In other words, it's changed direction, which is why when you look at a mirror, you see yourself perfectly, only there's a major difference. Everything is reversed, right? Yeah, if you had writing on your shirt, would you be able to read it in a mirror? No, it's backwards, right? I mean, maybe if you're super... But keep in mind that things don't have to be smooth to be reflective, and what we think of as reflective isn't always what? This white paper is perfectly reflective. Other than the ink, it reflects almost all the light that hits it. You know that white reflects things because you ever been out working in the hot summer day wearing a white t-shirt and then other than the gross sweaty factor of it, and then done the same work wearing a dark black t-shirt? Which one's way more comfortable? No, it makes an enormous difference. Do you guys not know this? What's the difference? Black, because black absorbs all that heat. It absorbs all those sun rays. If you watch like the Bedouin people, or people who like live out in the desert, they wear long flowing robes, and you might think like, oh, why are they covering up all the skin? Well, they have to prevent it from damage, right? But also you stay much cooler because if your skin is darkish, it will protect you, but it will also absorb heat, right? whereas a white robe will reflect most of that heat away, right? But they wouldn't never in a million years go out in the desert wearing a big dark black robe, right? Because what would it do to all the heat? Absorb it, and now it's stuck next to your skin. So why does paper not show my reflection? Well, because paper, if you look at it under a microscope, has a shape like this, and so when the light hits it, it isn't going to bounce off necessarily in a nice direction. In fact, if light were to hit this here, it's going to like bounce to there, and then from there, it's going to bounce like up here. Like the light goes just kind of every which way because the surface is really messy. Does that make sense? And so then when a ray of light that was kind of like that hits here, well, that's just going to reflect like this way. And so you just get light behaving in totally random ways, but it's still reflecting. Does that make sense? Here, this light might go and have like a completely bizarre path, right? Like it could go, oh, here I am.
We have to write that.
Oh, yeah.
What are we doing now?
You maybe don't have to get as into it as I am.
I did the other.
It's actually possible to trap light. We'll talk about that. Where you see how we have this reflected into a little spot where it can't get out? You can actually design mazes for light where you can shine a ray of light into something that it can't get out of, and it just bounces around in there pretty much forever until it gets absorbed, even by things that normally don't absorb light very well. But the point being, this is going to give like a smooth reflection, which would like give you an image, whereas this would give you scattered light. Paper reflects light, but it scatters it, so it goes everywhere. Which means, you know the other difference here too, which is if you want to see a certain thing in a mirror, you have to stand in a certain place, right? Because it only sends the light one place. It's a perfect reflection, right? So if you look at the mirror here, you can see your face, right? But if you walk over here and look at the mirror, you don't see your face anymore, right? Because the mirror can only send light in specific ways, right? Because it sends it perfectly. The white paper, everyone can see the white light from it, can't they? Because it sends it in every direction. It scatters it. Rough surfaces scatter light when they're reflected. Cool. So that's the first thing. Light can bounce off. The second thing we've already talked about, what does a black shirt do with all that light in the sun? It absorbs it. So light can be absorbed. And in this case, if that light comes in, it just strikes that surface and there's no more light ray. But note that for that to happen, the energy from the light is now in the object. And that can look like a bunch of different things, right? A black shirt absorbs sunlight and turns its energy into what? Heat. On the other hand, a solar panel absorbs the sun's light and turns it into? Yeah, specifically what type? You know this. Electricity. Good, yeah. A plant absorbs sunlight and turns it into chemical energy. It turns it into sugars. Does that make sense? So it can look like a lot of different things, but if we absorb sunlight, the energy is now in the object. And the most common way that happens is just heat. Mostly when light shines on things and it gets absorbed, they heat up. Does that make sense? And then the third possibility we talked about is light can bounce off, it can absorb, or it can travel through, right? And we call this transmission, right? All right, an example of this would be, here we have a glass window, right? Window. And over here we have the sun. And the sun's rays, just shine right through. I'm going to draw them all in one. I'm going to forget the sun. Let's draw a flashlight. Nobody has flashlights anymore because we all have the best flashlight ever in our phones. Big improvement. Sorry? Well,
You know what?
Aiden, you'd have done great in the 1950s.
It's actually on my bedside.
Oh,
Just in
I
case the
don't
power
think
goes
so.
out. Well, it's because actually I'm
No,
in the
no,
basement
no.
and I have my phone
No.
sitting.
You said you would have done great in the 1950s.
Mr. Orlando,
Yeah?
be nice.
How was I not nice?
You said you would do great in the 1950s.
Yeah.
Oh dear God.
You know what I mean?
And yeah, shut up. Don't even get started. Look what you caused, Mr. Orlando.
Come on, settle down, dude.
Yeah, tell her to settle down.
All right. So this is the basic idea here. Okay. Questions about that? Okay, now ready? What's light? We talked about what light does. Light hits stuff, it either gets absorbed or it reflects. It can go through things. It can bounce off things, right? All that stuff. It travels in a straight line. Some materials can make it change direction, like glass. Some things like gravity can make it change directions. But what we haven't yet talked about is really, what is it? We said it's energy, but how? What is it made of? What stuff is light? What is the stuff of light? Tomorrow we're going to watch a couple videos that I think explain this well. But this is really kind of esoteric. It's weird. Okay. Light itself isn't anything. That sounds weird. But light isn't a thing. It's not matter. It's not made of something. Does that make sense? Rather, it's like, here's the deal. The comparison we always make is this. Like, what is a wave out on the water? If you go in a wave pool, or maybe you have a swimming pool and you make a wave pool, right? By like just pushing the water up and down, you make waves. What is the wave? Well, it's just water, right? You ever think about that? Like the wave itself. But here's the weird thing. I'm sure you've seen this before, but like if you look at a wave, here's a flat piece of water, right? And let's say imagine we could make one little piece of water go like that, right? As the wave happens, if you send a wave along, so if I make a single wave here, right? There it is. And then the wave moves along, right? And now it's here. And then it's going to move along and be here, right? Like that's what's going to happen over time, right? The wave moves along the water. We've all seen that before, right? Does the red piece go with it? No water actually moves. Waves are weird. Look at me. Waves are weird because the wave moves through the water, but if the water doesn't move forward or backwards. The water just moves up and down. Does that make sense? The water just moves up and down. The wave isn't water. The wave is a thing that's happening to the water. Does that make sense? Okay. Why do we talk about this? Well, because light is also a wave, which is kind of weird to think about. But here's what it is. The universe contains energy fields. Energy fields. And specifically, there is a magnetic field.
Oh my goodness.
I'm gonna die.
It's possible. And there's an electric field. This is some advanced physics, and we're not going to get too much into it, but look at me. You've all used a magnet before, right? A magnet is able to take an object and pull it towards itself. How does it do that? Well, it does it by interacting with the magnetic field. Does that make sense? And a magnet works even out in the vacuum of space, So it's like, how do two things that aren't touching reach out and grab each other? And the answer is that the magnetic field lets the atoms in one thing interact with the atoms in another thing, even though they're not touching in any way. Does that make sense? And the electric field lets the electronic things happening in one atom affect the electronic things happening in something else, even though they're not touching. Chemistry is all about this electric field, right? Because we talked about pull on electrons, right? We talked about how an atom has a pull on electrons. Well, what that means is that an atom affects the electric field so the electrons want to move in one direction towards them if they're positively charged, or away from them if they're negatively charged. Does that make sense? So the electric field permeates all of the universe, and it allows magnetic things and electric things to interact from one atom to another. So light is just a wave. Light is a wave moving through the electromagnetic field. Yep. So light is a wave moving through the electromagnetic field. And how do you make a wave? How do you make a wave in water? Because water is just a wave, or what we call water waves are just waves moving through the field of water. We call that like an ocean or whatever. If you go into a still piece of water and make waves in it, what would you do? Well, you just have to get some of the water to start moving, right? Does that make sense? And to make a simple wave, if you just drop one drop or one stone or something in the water, you get ripples, right? You get a single wave that goes out, because if you make the water move, it's going to want to go back to where it was. But in doing that, it makes the water next to it move and then go back to where it was, right? And that makes the water next to it move and go back where it was, and that spreads out. Does that make sense? Well, this works the same way. Anytime you move water, you make the water around it form a wave, right? Well, anytime you move a magnet, you make a wave in the magnetic field. And anytime you move something that has an electric charge, you make an electric wave. Does that make sense? Well, electrons have both magnetic properties and electric properties. You can affect an electron with magnets, and you can affect an electron with other electric charges. Does that make sense? So anytime electrons move, they cause waves to form in the electromagnetic field, and this is light. So as weird as it is to say, anywhere there's moving electrons, there is some light being made. Well, wait a minute. What are you made of?
Skin.
Sure. Skin, bones. What's your skin made of? Cells. What are your cells made of? Molecules. What are your molecules made of?
Atoms.
Atoms. What are your atoms made of? Protons.
Protons, neutrons, and electrons. Subatomic particles.
Are your electrons moving? Well, we know they are. How do your electrons move? They move around in orbitals around the nucleus, right? Which means anytime electrons move, they make light. Does that make sense? Because all it is just this bouncing in the electromagnetic wave. You are sitting there right now with moving electrons. Do you know what you are making right now? Light. You are glowing right now. Seriously, in all seriousness. Right now, you are beaming light out of every little piece of your body. And so is your shirt and this coffee cup and that guitar. Everything in here is blasting light out into the universe. Why can't we see it? Kind of. Our eyes just can't see that level of light. By the way, our eyes would be way better at being eyes if instead of needing the sun's light to see, we could just see the light that things make. Doesn't that make sense? Right? Like, we need the sun or we need a light to see. If our eyes worked at a different type of light, we'd be able to see them. They make cameras like this. You ever seen an infrared camera? The cameras that, quote, see in the dark? Or heat vision cameras, right? Like a FLIR camera. They are able to see the light that people make. If you've ever seen one of these infrared cameras, and like when somebody's walking on the ground, like you can see their footprint on the ground and that disappears and see their footprint, because when they step on one spot, they heat it up for a little bit with their bare foot. You ever seen this before? The point being, anytime electrons move, they're making light, which means every single piece of matter in the universe is constantly making light. Is that a little weird? A little weird, right? Okay, but we know this too, because if we can make the electrons move a little faster by making the atoms move a little faster, we can change how much energy is in the light. And if you take a normal everyday object and get it hot enough, what starts happening to it? Say you take a piece of metal and you hold it over a Bunsen burner, hold it over a flame, put it on a stove, keep it going until it gets real hot. What will it start to do? Well, assuming it doesn't melt. We pick like a real strong metal, iron, where it takes a lot of heat to melt. Long before it melts, what's it start to do?
Color.
Well, what do you mean it changes color? If it doesn't change color, it starts to what?
It's hot.
And it starts to what? It doesn't just change color, it starts to... If we turn the lights out, I can't see what color shirt you're wearing, but would I be able to see a really hot piece of steel?
Yeah.
Yeah, because it glows. The truth is, it was glowing before. It was just glowing at a color that we couldn't see. But you heat it up, and all of a sudden, it gets to glow at a range that our eyes can see. Does that make sense? Heat up a bit more, and it'll change color again. It'll go, something first starts to glow, because its electrons are moving a little faster, which means it's making shorter waves. It's making waves faster. What do we see first? What's the first color we can see when something starts glowing? No, before yellow. Even before red-orange, if something starts to glow a little bit and you turn the lights out, it's a real dark red. Then it'll get kind of be a brighter red. Then that red will turn to orange. Then the orange will turn to yellow. Then the yellow will actually turn to white.
And then light blue.
And we get that blue and violet, right?
Yeah.
And we'll talk about why white in a minute. Does that make sense? And all that's happening is when you heat that metal up, you're giving its electrons more speed. Does that make sense? And as they speed up, let me ask you this. If I was in the water and I made waves like this, what would I see? Well, I'd see wave, 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 right? Well, what if I get moving faster? Now I'd see wave, 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 right? Same height. I'm not changing the height. I'm just changing how fast I do. Does that make sense? Well, now what if I went wave, 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 right? We'd see wave, 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 right? Does that make sense? Well, when we get electrons going faster, they make more waves. So we actually have just determined something. Not only is light a wave in the electromagnetic spectrum, but what we perceive as different colors of light have to do with how fast the wave gets made. When we say fast, what we mean is how quickly we go, here's another wave, here's another wave, here's another wave, right? When we scrunch the waves together closer, eventually they get close enough that we can see them. And the first color that we can see is the color we call red. So those are waves that are close enough together that we can see them, but then when we make them a little bit closer, we get kind of orangey. Does that make sense? And if we heat the electrons up so they're moving even faster, now the waves are closer, well, now we call that yellow. And even a little faster, this is where you actually should be seeing green and blue, but that green, we'll talk about why it interacts with other stuff. We tend to see it as white light when we heat something up. But then we get the blues, then we actually get these violets, these very kind of purpley, purple-blue kind of colors. And then the ultraviolet, though ultraviolet rays we can't see, though our skin sure gets damaged by them, right? The sun's ultraviolet rays. So let's talk about that. Because waves can have different properties, light can have different properties, what does that mean? So as electrons move, they make waves. The distance between the waves, between the peaks of the waves, are seen as different colors. And now I'm going to attempt to draw some waves. Ready? Whoa. And what we're going to do is have them get closer together. That was okay, I'm going to try again. Can I try again? You know what I'm going to do? Ready? I'm going to very gently give myself like a top line, a middle line, and a bottom line to work with. And that's going to really help my art. As you know, guys, I'm a very good artist. Maybe I just need a top and a bottom line. That should be fine. So we're going to start and say like, okay, what if the waves started out really far away from each other, but we have them getting closer? Well, all of a sudden we said the first waves that are visible are these red ones, right? And then we said as they get a little closer together, we call that orange. And then after that, we get to the yellows. And then if they get even closer together, we're going to see green. Which plants, you know, we think green light, we think of plants. And then blue. And then we get to these really kind of violet colors, which I don't even know if I have a good, that's a pretty good kind of simulation of that. And again, I'm sure. And then after that, we can't see anymore, but the waves could still keep getting closer and closer and closer, but our eyes can only see waves in this range. Does that make sense? We call this the visible spectrum of waves. Why wouldn't I put that below? Wouldn't below be a much better place for that? And to remember that order, we usually say that it goes red, orange, then yellow, then green, then blue. Some teachers include indigo in here. I refuse. I think it's silly. I just say violet. The only reason they include indigo is to make this a fake word, Roy G. Biv, which isn't even a word, so why bother? So I'm just going to rather say Roy G. Biv is kind of the way we remember this, but you don't need the I. Just, it's like a person. Oh, who's your tax guy? Who does your taxes? Oh, my buddy Roy G. Biv. I don't know. Helps you remember it, but there it is. Now, when we talk about how much energy waves have, well, if you go into a pool, would it be harder work to make waves that were far apart, or harder work to make waves that are really close together? Close together. So, no different with how electrons do. Which one of these waves have a ton of energy in them? The ones that are close together. Which one of these waves have less energy? The ones that are further apart. If you develop photography in a dark room, you have to have some light so you can see, right? So, because otherwise, like, it's very hard to work totally in the dark. In professional photo labs, that's exactly what they do. All the work is done completely in the dark. And those guys actually have to be trained to step into the dark room and do the steps of what they do, no vision whatsoever, because they want the best possible outcome. They want your photos to look the best, so they do it totally in the dark. That's where the best chemical plants in the world do. Now they do it with robots, right? Though now we don't even really develop film. But for home film developers, what they'll do is they say, okay, we need some light, and that light is going to further develop the photo. It's going to ruin the photo a little bit, but we want to ruin it as little as possible. Well, what kind of light should we use to make sure that we're adding as little energy, adding as few reactions to that as possible? We use a really red light in a dark room, and we put it as dim as we possibly can. Does that make sense? If you used the brightest blue light you could find, you would develop that. This, by the way, I'm sure you've noticed this. I just got a new phone charger for my phone that I keep on my bedside. And first of all, I don't understand why our things need lights to tell us that they're on. I think that's annoying. You know how I'll know it's on? It's working. It's doing its job. But okay, has to have a light to say it's on. By the way, nothing is worse than my grandparents have a TV that has a light to tell you that it's off. Thank you, off light. I couldn't tell that my TV was off by the fact that there's nothing on the screen. Oh no, I need a little red light down here to tell me that you're off. But what's even worse, now if they're using a little red light to say it's off, oh great. What light did they use to say it's on? A little blue light. Do you ever have one of these things, something in your room that has a little blue light to tell you it's on? It like lights the whole friggin' room up. It's this tiny little bulb like this. I lie in my bed and I'm like, oh my God, like you can see, I could read that, like I could read the title of that book over on the other side of my room. Ridiculous. By the way, lights at night are what keep you from having a good night's sleep. And anyone who tells you otherwise is lying to you. This is why, like in the phone era, kids, the amount of sleep kids get at night has decreased by like 30%. And you should lock your phone up after 9 p.m. It's ridiculous that you don't. Because, and this is true, do you know when your brain forms new neural connections? During sleep. And this, all the studies show this. You will be dumber for your whole life if you get inadequate sleep during your, this is true, during your adolescent years. You are actually impacting your lifelong intelligence measurably by staying up all night. Cut it out. Phone away. Lock it in a box. Go to bed. You'll go through a week of withdrawal where you feel awful and like you're really missing important things. And then something magical will happen. You'll be fine. And you'll be sleeping better. And you'll be smarter. And it takes us about, our body is used to going to bed a little bit after the sun goes down. That's what our circadian rhythm, that's what our body's been trained. So your body expects a couple of light-free hours where it has no bright lights before it's ready to go to bed. So don't put your cell phone in a box and then go to bed and be like, well, now I'm still wide awake. Yeah, put away a couple hours and then do something. Talk to a person. Play a board game. Go for a walk. Take your dog for a walk. Throw eggs at your neighbor who you don't like's house. I don't know, teenage stuff. Point being, you do that for a couple weeks, you'll feel better, you'll learn better, you'll be better in school, you'll be less irritable. Anyway, enough about that. So this is the electromagnetic spectrum. This is the light we can see. What if waves get even stronger than violet? What do we have here? Really violet light. What's the name for that? No. Ultraviolet. Good. So we have UV rays. And if we get even more energetic than UV rays, we get rays that are so powerful they will shoot right through your skin, as if it wasn't even there. But they won't be able to go right through your bones, which means if you made a picture with this kind of light, you could actually get a picture of somebody's bones. X-rays. X-rays are the same stuff as light. They just have way more energy than normal light. X-rays. And then what has even more energy than X-rays? Dr. Bruce Banner blasted by them. That's impolite. Gamma rays. You heard of those before? These are incredibly high energy rays. All right?
Will it ever stop? Or will it...
We call everything above a certain threshold gamma, but in theory they could get closer and closer and closer and closer and closer. On the other hand, what has less energy than red? Well, just a little bit less than red. We can't see it, though your dog can. And the camera at your back door that you use to see if anyone's breaking into your house can see it. What do we call just below red? Infrared. Maybe you've heard of IR light? Below infrared, does anyone know? This has a really neat property. It's actually low energy, but it happens to make water molecules vibrate. So if something has water in it, you can shoot these at it and it will heat up. What kind of waves? What kind of rays? Microwaves. Microwave rays.
He's joking.
Don't die. Don't die. Jesus did it to you? I don't believe it.
I didn't see
You said Jesus. Anyway, and less energy than microwaves. We use this to send communication all day long, including on your phone that's keeping you up all night so that you're sleepy all day. Radio waves. All right. And everything you call everything else, like Bluetooth is just a radio signal, Wi-Fi, the Wi-Fi band is just a radio signal. Your cell phone, whether it's 5G or LTE or 3G or 4G or whatever it is, it's all just radio waves, different frequencies, but they're all just radio waves, which means this is weird, but like the signal that your phone sends out to talk to other phones, to talk to the cell phone station, the signal that your Wi-Fi router shoots to talk to that, the signal that your earbuds send to there are all just light. All of this is all light. Does that make sense? All of this is light. Radio waves are so big that they just go right through soft stuff, which is why, a Bluetooth signal can go like through your body. It doesn't matter if your phone's in your pocket. They don't have to see each other the way visible light would, because radio waves can just go right through your body. In fact, they don't even go right through your body. It's a little weirder than that. They go right around your body, as if your body wasn't there. So there we go. Now, this is drawn for you on the next page, but I always think it's helpful there. And when you see this diagram like this, what they're showing is that because when electrons move, electrons are both little electrical charges, but they're also little magnets. Light, being the result of moving electrons, is a vibration, is this oscillation in the electric spectrum, in the electric field, and the magnetic field. And they usually show those by being kind of 90 degrees offset to each other to make it look there. All right. Tomorrow, we're going to look at how the visible light we see can be broken up, all right, broken into pieces. You, put that away. Right away. Put it away. But what I want to show you is this. Oh, we're not done. I got 5 minutes and I'm using them.
I have it right here.
Is with this wave, there's some words we're going to use a lot. Okay, so I just want to make sure we all know them. So if we draw a wave like this, a wave has a central line, right, that kind of goes above and below and above and below. So the first thing we want to talk about is a thing we hear a lot, the wavelength. And the wavelength of light, I did not do a good job drawing that, so I'm going to redraw this just so it's not a crappy drawing. The wavelength of light refers to the distance between the first wave and the second. The distance between two waves we call the wavelength. So if I draw a line from here to here and were to measure it, that's the wavelength. This determines the color of light. And when I say color, I mean the type of light, because we see colors for the visible spectrum, but again, keep in mind, really short wavelengths we call gamma rays, really long ones we call radio waves. A radio wave is actually way bigger than you are. Radio waves get upwards of a whole kilometer. It's kind of weird to think about.
Excuse the interruption, folks. On today's cafeteria menu, we have Korean sweet red pepper soup for $2, assorted subs and sandwiches, taco salad for $5, jerk chicken with roasted potatoes and a pita for just $5, and right now we have our Moolah Palooza. While supplies last, every large chocolate milk purchase will give you the chance to win a free meal from the Eastdale cafeteria. We're running this from December 1st up until the 7th, which is tomorrow, may I add. One winner will be
This guy's good.
at the end of every day, and ballots are being refreshed.
He's good.
This would be you.
Thanks for listening.
No, I'm so awkward.
Hey, well,
I'm so awkward over the PA. You'd be good over the PA. You're enthusiastic. I try my best every time I do an announcement. I feel like every time I do an announcement, I sound like an idiot.
Or the bell ring, honey.
I'm sure it happened. Anyway,
I don't know.
so this wavelength, if you look here, that's these numbers up here. And if you look, a 1 meter long wave would be in the radio range. After that, we start to get really small. From nanometers all the way down to gamma rays are incredibly small. Yeah. We'll talk about it later on, but this is important to know that wavelength determines the color of light. All right. And most things that produce light produce rays of many different wavelengths. Most light is a blend. It's not just one color. And that's what we're going to do tomorrow, is tomorrow we're going to look at things that make light and try to break the light they make up into different pieces of it. How many of you were here for grade 8 day years ago? Nobody? Nobody here took a tour of Eastdale? You were here. Did we put your cell phone under a microscope? That's usually one of the things we do that day. It's usually fun. Or have you ever done that before? Because that is actually pretty instructive of how it is that we make light. Anyway, have a great day, guys. We'll see you tomorrow. Be kind to each other. Don't do anything Cindy wouldn't do.
It's a pretty big range.
Right? Well, this is what I'm saying.
All the students, please come to the office. Noah Summers, Talia Garcia, Haley Cutler to the main office.
Shirley, how we doing? That good, eh? Is the last truck back today?
No.
Still not.
He likes me to